Next thing we want to talk about is rotational equilibrium. Now this is something also that you somewhat know intuitively. The idea of rotational equilibrium is you want things to balance out. You have a pivot spot, maybe it's a fulcrum, like this fulcrum's positioned perfectly in the middle of maybe a seesaw here, and I got two kids on it. And we want these two kids to balance out. That way they can easily push up from the ground, and that's the only force. That's the only thing making them go up and down, is them pushing up from the ground as they move, instead of actually one weighing so much more or sitting further out and weighing more, thus getting more torque and pulling it down. So rotational equilibrium is all about balancing things out. Now, the instructions I have for rotational equilibrium only work here if all the forces are pointing the same way. And the problems we're going to do, the forces are pointing down. Whenever you have forces pointing down and up on something, then everything gets a little off. Or if the pivot point isn't in the middle between them, if the pivot point's all the way over here, you're going to have a force pointing up and a force pointing down. Things are a little off. We're going to talk about that at some later time. Now the point here is we want all the torques to balance out, because we already said in the previous video that if you have a further distance out, you could actually use less force to obtain the exact same amount of torque. So a lighter kid could just sit further out on the seesaw than maybe a heavier kid and still be able to balance the entire thing out. The point here, rotational equilibrium. Add up all of your torques, set it equal to 0. Now, steps. Draw a picture. Choose positive and negative for directions, specifically with the distances from the fulcrum. We're going to pretend the fulcrum is at 0 for how we're trying to solve these problems right now. We will make an adjustment later whenever we have forces that are going both up and down instead of just down on this. But assuming this is 0, choose positive and negative. Now I'm going to choose to the right to be positive and to the left to be negative, and go ahead and apply that to the distances I have. So this would be a positive 1.3, and this would be a negative 1.0 meters. Next step that we're going to end up doing here, add up all of the torques, and the fulcrum is the pivot point right there in the middle, by the way. So that's your 0. Positive going to the right, negative going to the left. So this is negative 1 meters away from the pivot point. I do need to point that out back from the first video. All distances are measured from the pivot point. So if you have something that goes to both sides, the spot that it's going to turn around is going to be the fulcrum, right? Or wherever it's trying to turn, right there in the middle in this case. Sometimes you'll see the fulcrum offset a little bit one side or the other. Add up all the torques and set them equal to 0. Now to start out with, I'm just going to label objects. I'm going to call this kid kid 1 and this kid kid 2. And sometimes that's a very helpful thing to do, is just to go ahead and label what you have, objects 1, object 2. So the torque of 1 plus the torque of 2 equals 0. Just adding them all up. Now if there were more objects, it'd be torque 3 plus torque 4 plus torque 5, however many torques you have. Torque 1 plus torque 2 equals 0. Then we're going to start solving. Next step is to actually substitute in the equations for torque. So torque is force times distance. So I have force 1 times distance 1 plus force 2 times distance 2. Now your brain might be screaming, one of them has to be negative, that way they balance out, or I should put them on either side of the equation. Yeah, but one of them is negative. Notice the negative displacement for 1. So as I substitute in numbers here, it becomes not that big of a deal. Kid 1 has a weight, a force of gravity of 300 newtons. The problem says right here, notice newtons is a force. Also check out sig figs. There's a dot there, so that's going to be 3 sig figs, 2 and 2. So it looks like our lowest number is 2. We'll round to 2 here at the end. 300 newtons. Distance 1 is negative 1.0 meters. Plus force 2 looks like what I'm looking for. How much does kid 2 weigh? So I want to solve for F2. And D2 is a positive 1.3 meters, and all that's equal to 0. So now I just need to start solving through. So I have negative 300 here, plus F2 times 1.3 equals 0. Add my 300 over to the other side. Notice I'm adding because that was a negative 300, and then divide both sides by 1.3, and I come out with F2. So kid 2 has to have a force of gravity or a weight of 230 newtons. Now, a problem where you're not actually given the forces pushing down, instead you're giving masses, actually works the exact same way. Just the forces there are going to be the force of gravity on a mass times 9.81, where they give you the mass and you have to multiply that by 9.81. Now, you would actually notice that the 9.81 would cancel out, but I want to get in good habits, so actually deal with the forces, not the masses in this. So sum of all the torques equals 0, and I'm going to choose positive, negative. Positive to the right, negative to the left is the way I'm choosing, so that's a negative 0.35 centimeters. Now, I also also wanted to set this up. I'm making this on a meter stick with a fulcrum right there in the middle. So sometimes you won't see distances given to you measured back to the fulcrum. Sometimes you'll see distances, if it's a meter stick, given to you from the end of the meter stick. So they would have said, hey, the 300 gram mass is 15 centimeters from the end, and the fulcrum's exactly in the middle. And so you'd have to say, oh, that's 50 centimeters here, so then I need to subtract. 50 minus 15 gives me my 35, and then I can pick to the left being negative, to the right being positive. And in this problem, I'm looking for at what distance must I place a 400 gram on the other side. They might give you things in terms of the entire meter stick. So adding up my torques now, torque of the 300 gram plus the torque of the 400 gram is going to equal 0. Then I can just substitute in what torque is, force times distance for each. And now it's just plugging in all the numbers. So the next step, actually substituting things in, I have to realize this force here is not 300 grams. That's not a force. It's the force of gravity. And force of gravity, gravity pulling on that 300 grams, is mass times gravity. So you can already see this is going to become 0.300 because grams to kilograms. Technically, I could leave it at 300 and it would all cancel out. And notice I also converted my centimeters to meters here also, 0.35. I could have left that 35 and it all cancel out, but I'm just trying to establish good habits here, converting back to base units. And also making sure that I include this as the force times distance, not just the mass. Good habits. And now all I'm left with, after I substitute mass of 300 times 9.81, that's the force of gravity on it, and the negative 0.35, 35 centimeters negative, because it was going the negative direction here. I declared to the left negative, where 0 being the fulcrum. Plus, here's mass of the 400 times gravity, 9.81. That's the force of gravity on the 400 right there. That's why I had to do mg times d, so F here, mg, times the distance is what I'm looking for, distance of the 400. Now I'm going to multiply these together, subtract over, and divide. And whenever I actually go through that algebra, right, multiplying all this together to get negative 1.03, notice the negative sign with the distance, and multiplying these guys together, that's the force of gravity, 3.924, right? Add the negative over, divide, I come out with then 0.2625, so with 2 sig figs, 0.26 meters, because my distance was the smallest number, 0.26 meters, or 26 centimeters for the distance that you would actually have from the 400 grams, which should make sense here, because 400 grams is heavier, so it shouldn't be as far out, giving you even more torque if it was far out. It should be a little bit closer in to make these two balance. The lighter one has to be further out for it to balance out.